All right, welcome to the Lightline Continuing Education Seminar. For those of you who tuned into my session last week on why we killed the can, there was a good chunk of that session. We talked about thermal testing and what safety is and how you approve it, and some really good questions came out of that presentation. And we thought, hey, we're looking for more content. Why don't we do a deep dive into how we actually test products and how we actually get certification on products? So before we get into that methodology, one of the questions that there's always so much confusion around in the world is, do you have UL certification? Is that you, or is that CSA certified? Oh, that's Intertech. Is Intertech the same as UL? Is that the same? Like, what's going on with all the certifications? So now that we all have time to listen and learn about it, we can dive into that a little bit. So what happens is, when we build a product, we have to make sure that that product is safe. In order to make sure that it's safe, we have to make sure that it meets certain standards. Each country has a set of standards that are legal in that country. In the old days, CSA was the standard for Canada, and UL was the standard for the United States. Right around the time of NAFTA, the first one back in '91, we had what was called the harmonization process. So what that meant was that we split up the organizations of UL and CSA into two parts. One part of the organization writes the standard, and the other part of the organization tests the standard. So what that means is that CSA writes the standard for Canada, UL writes the standard for the United States, but the testing department of CSA can test to the UL standard, and the UL testing department of the United States can test to the CSA standard. To make it even more confusing, there are other laboratories that can also test to the CSA and the UL standards. The number 3 player in the industry is Intertech, or the ETL mark. So what ETL does is ETL can test and certify to the UL standard, or to the CSA standard, or to plenty of other standards that are out there. They're actually a testing laboratory. They don't write a standard, they test to a standard. The other thing that happened was there was a harmonization process where the UL standard for the United States and the CSA standard for Canada were, to the vast majority, for all intents and purposes, harmonized. That is, they are the same standard. So UL 1598 and CSA 22.2 number 250 are functionally the same content. That's the standard that lays out all the criteria for a luminaire to be certified. Here at Lightline, we are a level 3 satellite lab for Intertech. So what does that mean? That means that we are certified as a laboratory location under the umbrella of the ETL organization, and we are certified to test our own fixtures to a variety of standards. The standards that we're qualified for are posted on the door on our fancy 8.5 by 11 piece of white paper. And broadly speaking, they're UL 1598, which is general luminaires, UL 1574, track lighting, UL 2108, low voltage lighting systems, UL 8750, anything that has to do with LEDs, UL 153, which is portable luminaires, anything you can plug in, and CSA 22.2, LED equipment for lighting applications. And I don't really know what that standard is, but we're certified to test to it. So what level 3 means is that everybody who's authorized to work in this laboratory is trained by Intertech, and their skills and processes are regularly audited, and Intertech regularly audits our equipment, our process, and our documentation, as well as a host of other things. And on a quarterly basis, we give them a ton of money. And what that means is that we can do our own fixture testing in our building, submit our data, they review it for consistency and for general, to make sure that we're doing it right, and then issue us our certification on our product. Now, that's just a part of the certification. All UL and CSA standards are interested in, or I should say the primary things that UL and CSA are interested in are safety related, which basically boils down to the thing doesn't fall apart, it doesn't overheat and burn down buildings, it doesn't electrocute you when you try to use it, and it works. There are lots of other standards that are relevant in the market that are not governed by CSA and UL standards. For instance, Energy Star, or photometry, or Title 24, or the list can go on and on. Radiation, so FCC or ICES, to make sure that we're not spouting out stray radiation. So our products are all tested to those standards. We have the equipment to do the vast majority of those tests in-house, and we have the authority in-house to approve our products to the applicable safety standard. So I hope that was clear, and anybody that's still with us at this point in the presentation, kudos. It means that you actually get to learn how to do it. But that's sort of the broad umbrella. CSA and UL write safety standards. We test those standards. We submit our data. We get our approvals, and then performance standards that are outside the specification of safety are governed by other organizations. We test, but they have to be retested by outside organizations. So our photometry, for instance, is tested by a third party when we submit for DLC approval or Energy Star approval. So what is involved with doing safety? Safety and lighting basically comes down to don't let it burn down a building, don't let it electrocute anybody, and don't let it fall on anyone's head and hurt them. So that being said, we have the apparatus to test thermals, electrical and mechanical. So a thermal test is basically the process of taking a light engine, connecting a bunch of thermal probes to it. That's these wires right here. Burying it inside a box of specified dimensions, and either burying it in insulation if it's a type IC fixture, or not burying it in insulation if it's a non-type IC fixture. Hooking it up to the computer and letting it run for 8 hours and measuring the thermal rise. What we're attempting to do with this thermal rise is have this exponential increase and then flatten the curve. We're all into flattening the curve. I saw a great meme on Reddit, for those of you that are also nerds out there, that was this graph, time spent looking at exponential curves. February, March, April. Okay, good. So we have one person laughing. Everybody else is wearing a mask in the room, so I have no idea if they're laughing or not. But the point is that we're all going squirrely at home. So thank you for watching me give a tour of our laboratory. I put on pants today. I'm very proud of it. So what we're trying to do is have this nice exponential curve where the temperature rises, stabilizes, and then flatlines. If that curve keeps rising, that means that the fixture is overheating and might burn down a building, and it's not approved, so we have to change stuff to make sure that it stabilizes. And not only stabilizes, but stabilizes below the specified value. So the most important value, the probably three most important values are the outside of the thing can't get too hot, so if you touch it, you don't hurt yourself, or if it's touching wood frames or construction, it doesn't burn down the building. The second most important temperature is the temperature on the actual LED chip itself, to make sure that it's running within specifications and it doesn't burn out. And then the probably third most important is the temperature inside the junction box, to make sure that your conductors, your wires, aren't overheating and gonna cause an electrical fire from insulation melting. All the other temperature points are important. Oh, and any plastic parts stay within the RTI index. So basically the plastics don't overheat and melt and drop on hot flaming plastic on people, because that's also not an approved construction. So that is the good chunk of what we do thermal testing. We also have our specification surface mount test box, where we hang weights from fixtures to make sure that they don't fall off the ceiling. That's an important thing. And then measure the temperature on the ceiling. So if you had a wood ceiling or gyprock, to make sure the actual building itself doesn't exceed temperature. So after we've determined that the fixtures are safe and secure and sturdy, so we've done all of our mechanical and thermal evaluation, the next step in the process is to move outside the scope of UL and CSA and move into the scope of what people really care about, which is, does it flicker? And is it dimmable? So the next step we have is this wall of dimmers. And this wall of dimmers is really neat because all the dimmers are just held in with 2 screws like any dimmer. The back panel flips open and we can swap dimmers in and out. And what we have here are the dimmers that our OEM partners have told us that they are actively promoting for their LED products going forward. So we are in regular communication with Lutron, Leviton, I guess Eaton Power, and our friends at Legrand, Pass and Seymour. And that's, I mean, I shouldn't name names, but they're the ones that told us. So if anybody else makes a dimmer and wants to be on our list, send them over. So what we try to do, or what we do in this department, is we'll take a luminaire and we will hook it up to our board here, and then we dim it. And we check and see if it flickers. And the first test is you look at it and you check and see if it's flickering. And if it's flickering, then it fails. It means that it's not compatible with that dimmer. The next step is you got to hook up 2 of them and do the same thing. And then you got to do 3 of them. And then you got to do 4 of them. Because if any of you guys watched my presentation on dimming, what happens is when you start hooking up dimmers, you start creating this turbulence in the field, this harmonic this waveform distortion. And dimming LEDs is really tricky to do. And the drivers do all kinds of really cool stuff. Check me out on YouTube if you want to find out what the driver's actually doing. But the point is that each individual fixture on the line creates its own little ripple in the power, and you can have one and it's fine, and you can test the max, and all the ripples are sort of in harmony and synchronization, and it's fine. But we sometimes have fixtures where like 1 is good and 12 is good, but 7 turns them all into a strobe light. So the only way to find that out is the hard way, which is basically line them up on the bench. Pull them up and down, make sure that the entire system is compatible, so you can put as many up and down. And don't think that it happens automatically. It doesn't, and we regularly discover things where like 7 fixtures flicker, but 6 and 8 don't. It's annoying. So then you have to go back and redesign your drivers, and that means that you have to redo your thermal test. And then that's why things take a long time to come to market if you actually want them to work. And that's one of the other things that you get from Lightline that you might not get from Amazon, is people actually verifying the entire thing actually works. So we go through the process. Check the dimming, check that it all works good to our eyes. Once it's like, hey, oh yeah, cool, I don't see any flickering, then we bring it over to the machine. And the machine is a sensor and a computer and the screen. And what that does is that actually tests 2 flicker standards that exist, none of which make any sense. That's not strictly true. They all make sense in their own world, but there's really isn't a very good flicker standard, because all the flicker standards basically say, hey, we want to test and make sure that this thing doesn't flicker in a normal circumstance, but none of them account for the dim circumstances. So even if you're in Title 24 or any of those other things and it says dimmable, they don't test flicker when it's dimming. They only test flicker when it's in the undimmed state, which is annoying, but that's not what we do. We just sort of apply the standards to them when in the various dimming states. So we'll test at 100, we'll test at 75, we'll test at the minimum, and make sure that there isn't any perceptible flicker or an unacceptable amount of imperceptible flicker. So what does that mean? Everything flickers a little bit. The question is how fast and how frequently, and by how much. So there are minimum levels set, which are well outside what's perceptible by a human being. But we use generally the Title 24 California Electric Code standard for determining what the maximum amount of variation in light output is. We're going to do another seminar like exclusively on flickering, because it's really interesting if you've already gone through your entire inbox and your Netflix watch list. Then you can watch lights flicker and say, that's interesting, we're going to do that. Yeah, that takes up a giant chunk of our time. Now, the question that those of you who know a lot about lighting is, hey, how come you don't have your flicker device inside an integrating sphere. Why are you doing this in open air? Like, is that going to be accurate? And the answer is, let's think about what flicker really is. Flicker is the difference between your peak light output and your bottom light output over time. So what this device can measure is it can measure your peaks and valleys of light output. We're not trying to capture all the radiative energy, all the lumens that come out of the device. We just want to know the peaks and valleys, compare them, and see how often they change and by how much. We have discussed thermal evaluation, which is don't burn down the building. We have discussed mechanical evaluation, which is don't let it fall on people. We've discussed flicker evaluation, which is don't let it annoy people. And now we're into, okay, all the things we shouldn't do. Now we're getting into the things that we should do, which is how much light does it give? And where does the light go? And what is light? And what is color? And there's a great XKCD on that if you are a nerd like me. You can Google it, XKCD, what is color? Have fun. So this device is what's called an integrating sphere, or a lumen ball. I always thought that would be a great name for a lighting company, lumen balls. But anyway, so what does this thing do? All right, so this is an integrating sphere. We have a light fixture inside a sphere. And the sphere is coated with the most expensive can of white Tremclad you can buy, because you actually have to have a certification on the Tremclad to because it reflects all the light in the sphere towards a single point. So what does that mean? Well, what it means is that we are blending all the light that comes out of that fixture and producing one measurement. So whatever comes out of the integrating sphere has a total number of lumens, has a average CCT, has an average peak and valley on your waves, and all these other cool spiky plots that you get on your IES file. We'll probably do a webinar on how to read an IES file and how the numbers, how we test and correlate to it. But what's interesting about this is this gives your total numbers for a given light fixture. What it doesn't do is give you any information about the spread of the light. The spread of the light comes out of what's called a goniophotometer, which is a fancy way of saying light angle measuring device in English. But this is so integrating sphere. We take a light fixture, we blend all the information into a single point, and then say this thing has 3,000 lumens at 27 watts for an average CCT of the 3000K, 3124, with a CRI of 92. But let's say that this was like a halogen light bulb from back in the day where you had pinks and greens and stuff spitting out all over the place. It's not going to tell you that, hey, it's got a pink halo around the edge, because we've blended and taken an average of all the light together. If we want to know how that light is dispersed, we have to go into the device in the next room, which we're going to hit in just a minute, because that'll give us, that's the goniophotometer that'll give us how the light's spread out. So information that we get out of the device voltage, the amperage, power factor, the watts, and then we get a fancy report that looks like that. They're available on our website. You can see them. And this is how we measure the actual light that comes out of the fixture to produce half of the IES report. Okay, so the other half of an IES report or a photometric report, the part that is more interesting to lighting designers out there, is not so much what's the total amount of light that comes out of this fixture, but how is that light distributed? Where does it go? Where does it come from? So we generate what's called an IES file, which is a text file which can be imported into AGI 32 or Dialux or a variety of other architectural modeling CAD programs. And what it is it's a a text file that has a matrix of how much light and what the color is of that light at the various distribution points. So what you can do is you can take that file and then you can drop it into a piece of computer software, and you can model how much light a given fixture is giving you in your actual space, and then you can determine whether or not that individual luminaire is suitable, or how many luminaires you need in that space to achieve your lighting targets, or if you're well overlit. And that's generally the number one thing that somebody asks for when they want information about a lighting fixture is, hey, can I have a data sheet which gives you all the electrical and mechanical parameters, and then can I have an IES file which gives you a model of the light that comes out. So how do you actually, when you get an IES file, nobody really knows, some people do, but some people, the questions out there, are they real? How are they produced? So this is how IES files are actually produced. We have a dark room, we have a machine, we have a light fixture connected to the machine. Then at the other end of the room, we'll just pan slowly through the blackness and darkness. We have a sensor on the wall. So what this machine does is we mount a light fixture to the actual machine. So the light makes a wave past the sensor, and we measure the light that comes off the machine, and then we rotate the fixture and we pass it back and forth, and we can do generally 8 or 12 passes through the sensor to generate a three-dimensional web of the light that comes out of the fixture. We're going to post a link to the manufacturer of the machine. They've got an awesome YouTube video on how the thing actually works if you want more information. Viso Systems, I think this is the best goniometer on the market for a bunch of reasons. That's how we do photometric analysis of our fixtures. We generally do photometric analysis for two reasons. One is for evaluation of the product during the R&D phase, and then the second is for marketing efforts and sales efforts when we're actually in production. So if you're looking at Lightline products and you're like, hey, can I get an IES file? It's not on the website, I don't know what to do. Just reach out to your local rep or regional sales manager, and if you have a particular build on a fixture that needs an IES file, let us know and we can bring it downstairs into the black hole room here and fire it up and kick you out the data that you need for your project. So the next evaluation that we have the apparatus for in our lab is wet location testing. So going back to the beginning, remember how there was a bunch of different standards that were out there in organizations? There's CSA and UL and Title 24, et cetera, et cetera. Well, when it comes to wet location, there are two standards. There's wet location evaluation from a safety perspective, and then there's ingress protection from a performance perspective. So when you're looking at a data sheet in North America, we evaluate to the UL or CSA standards, which is basically three ratings on a luminaire: dry location, damp location, and wet location. When you're looking at outdoor type luminaires or specialty luminaires, you might want more information, which is controlled by the IP scale or ingress protection. The IP scale gives details about how much water can actually enter a fixture, or how much dust can enter a fixture, and that's what those two numbers in the IP scale are for. So IP65 says that you have tiny, it's protected against dust the size of talcum powder or baby powder and high pressure water jets. But when you look at a data sheet or a safety sheet for a fixture and it says suitable for wet locations, all that means is that the fixture itself, if it's in direct contact with water, will remain safe. And that can be from two ways. One is that it's sealed against water coming in according to a certain standard, or the second is that it's actually equipped with drain holes, so if water does go in, it can drain back out and doesn't cause the fixture itself to short out. So we're certified to test to wet location rating, but for fixtures that we have that require additional IP ratings up on top of them, we send those out to third-party labs. So the way you measure whether something's dry, damp, or wet is you hook it up into the ceiling or the apparatus, we turn on the water, we let the water soak for 4 hours, and then we hit the fixture with 4,000 volts. If it doesn't short out, We are good for wet location testing. There's lots of other details if anybody from UL or Intertech is actually watching, but for everybody else, that's the broad brushstrokes, is you put the fixture in the shower, let it get wet. If it doesn't short out and it keeps working, and there's no, then you are certified for wet location testing. So thanks very much for coming on the tour of our lab. Hopefully you guys, I was able to help you understand what the various letter agencies, ETL, UL, TUV, are for, how the certification and testing process works, the actual steps that we go through to evaluate and certify a luminaire. We're going to be playing this video live in real time at one of our upcoming webinars. I will be standing by to answer questions after the presentation online, so if there's anything that was unclear, by all means, submit the questions. Laura will read them out to me, and I'll do my best to answer them. Thanks very much. Thanks for your time. Stay safe, stay healthy, and let's hope that we get back to work and I don't have to wear gloves in the near future.